Realization of the okay.
Thank you, Rafael. Thank you, Philip, for the invitation. It is a pleasure to be here with you. And also with my presentation, my goal is to show a little bit what we are doing here in Portugal and maybe create some bridges between both groups, okay? Because I believe there could be some topics of interest of each other. So, should I start the presentation and share my ecran?
Please, doctor, yes.
Yeah. Okay, today the title of this presentation is Numerical Modeling of Thermochemical Systems. And with this presentation, I will try to do a slight overview of some of the activities that we develop here in Portugal. This presentation has the logo from the Fundação para a Ciência e Tecnologia, that is the foundation that grants our research in Portugal, and also the logo from Instituto Politecnico of Portugal, where I serve as a senior researcher. So we have several areas of action. Our main core of research is numerical modeling, namely computational fluid dynamics. And there's a lot of areas where we apply this kind of methodology. For example, thermochemical processes, combustion, gasification, pyrolysis, but also in every area that includes some kind of fluid. For example, even fuel cells is an area of our research. So in gasification and combustion processes, we do not only model the processes, but also we try to understand the kinetics, the thermodynamics of the processes, and we interact with several groups that provide experimental data for the validation of our numerical modeling. So this is a potential bridge. For example, as we study the gasification of biomass, for example, we do not have the expertise of catalysis. And for instance, a group that works or deals with catalysis related with gasification of biomass or other kind of feedstock, it's a nice contribution for us because we are capable to do this kind of simulation and try to predict better conditions. So, of course, after modeling the process, what we do later is try to optimize the operating conditions. To do that, we use a lot of statistical methods and approaches in order to find which is the optimum spot of any process that we are dealing with. After studying the process, optimizing it, we try to understand if the process is profitable or not. So our last step is always to try to provide some technical economic analysis and try to show companies that are working with us if the process makes sense or not, and if the suggestions that we are trying to identify are useful for them or not. This is an important topic because we work with a lot of companies, and that's also a way to fund our work. So as a last choice for them, they want their processes profitable. So we have a great focus on it. Finally, we also deal with combustion simulation in diesel engines. And specific in this topic, we are dealing with the possibility of using ammonia in internal combustion engines. This is very recent, but as you probably know, in the maritime, in boats, they are starting to adopt solution of using ammonia for their engines as they transport large quantities around the world. So this could be a synergetic solution and very interesting for them. Also, and after studying the possibility of using ammonia in the engines, we are also studying the possibility to replace ammonia for several quantities of coal to deal with the coal phase out that the power plants around the world are feeling right now. So these are more or less our main areas of action, where we deal basically, we provide numerical models for partners and we try to receive from them experimental data. So it is work of a team, of different teams, and that's why I privilege so many partnerships, because it is very important. For one way, our students can learn from the experimental data and from the other research groups, and for the other hand, we can provide them numerical inputs that could be very interesting, and also engage the students in numerical simulation. So my strategy for this presentation is now try to show what we can do with this kind of simulation and how can it be useful to understand the processes in the industry and even at the research level. I didn't mention before, but if you want to interrupt or make questions during the presentation, please be free to ask them, okay? So one of our works was to understand what is happening in terms of hydrodynamics regarding biomass gasification. And using computational fluid dynamics, we can understand how the particles interact in terms of mass, momentum, and heat transfer inside the reactor. This reactor is a pilot reactor, but already with 75 kilowatts. So it is more or less big with two meters. And it is very interesting to understand, as the system is comprised for millions of particles, how we can try to understand this kind of interactions and have final outputs as pressure, temperature, how they occupy the different parts of the reactor, because knowing that we can improve the process and we can have better outputs or thermal management wherever. So in this work that was published at Energy Conversion and Management, we tried to do an experimental and numerical study regarding the hydrodynamics of a biomass gasification reactor. At the right side, you can see the fluidization curves, okay, to understand the pressure inside the reactor. One of the biggest issues that we have when we are modeling fluidized beds like these reactors is that the commercial solutions do not provide the correct fluidization conditions. So we have to develop our own code and insert in commercial solutions to predict exactly what is happening inside the reactor. And that's why this kind of work is important, because with our code, in-house code, we were able to represent what is happening at a reactor at this scale. And we can do the same for industrial reactors. I can tell you that if you do not include this kind of code, you could have errors much more than 100%. So it is very important to understand how we can do this kind of simulation, okay, to be very accurate and to use it in industrial partners. So this is with our numerical simulation and aggregating the several frames that we have on time, we can do like videos from the simulation. And this gives the idea how the particles are inside the reactor at the bottom, where is the reaction happens. The hot zones implies that there are more particles at that zone. And of course, the other colors, green and blue, means that there is no particles at it. So we can understand exactly when we are inserting the feedstock and the oxygen stream, what is happening in terms of hydrodynamics and movements. And it is very interesting. This is a very simple video, but we can do it for a 3D reactor and for the whole reactor in itself. So this is just to show the capabilities that are allowed if we can use this kind of simulation.
Valter,
Yes.
can I interrupt you for a second? Okay,
Yes,
you're
yes,
going
please.
to show the. Could you make a comment about the what is the gasification process and what is the input and output expected for energy recovery, and what is meant for? Because some of the students here are not very familiar with the gasification processes.
Okay. Gasification is an alternative for combustion that is basically to incinerate some feedstock, biomass, coal, wood, whatever. Okay. The great problem with combustion is the environmental footprint. Okay, because you can release a lot of particles that are clearly undesired for the environment. So we can do very closely to the combustion, but with slight differences to alleviate this environmental footprint. And this is called gasification. The great difference for combustion is that in gasification, we are under stoichiometric conditions, okay? We put oxygen in an amount that is not at the stoichiometric condition, okay? So we put less oxygen, let's say. And with it, we have not only gases as the product of the entire process, but also we can also have other products. And the outlet gas is called syngas, okay? This syngas could be used as a gas, or if we apply other processes, we can obtain liquids or other kind of products. It's a very flexible output that we can have and we can valorize. In terms of efficiency, if well done, gasification could present an overall efficiency that is superior to the combustion. Still, there is a lot of optimization to do to get this. In general power plants, when we have combustion, for example, coal combustion, we have an overall efficiency regarding 25% more or less. If we go for gasification, the process is more expensive, but we can reach about 40% of overall efficiency. It's not too much, but if you think about, we can increase about 15%, what could be substantially, and alleviate the fact that the process is more expensive. In this process, both in combustion or gasification, we can use catalysts to improve the process. And this is, once again, where we are also looking for partners to provide us different kinds of catalysts in order we test and understand what is the better catalyst for each type of feedstock, for example. Regarding the thermochemical processes, there is also another very known method that is pyrolysis. Pyrolysis is more or less the same process, but we reduce the amount of oxygen to approximately 0. So basically, we have no oxygen inside the reactor. And the big difference here is that at the outlet, we have liquids and condensates and not a gas, like in the case of the combustion or gasification. Summarizing, with gasification, we have increased overall efficiency. Okay, the process is more expensive, but on the other hand, it's cleaner compared with the typical combustion processes. I hope, Philip, that could be more or less clear. I don't know if you want that I can explain a little bit or not, or if is it okay?
Yes, I think it puts in the context all the work. So the group now is aware on what is the gasification process. And now, as you mentioned here, the municipal solid waste gasification, so they will really see the importance of these technologies. Thank you.
Okay, thank you. Yes, exactly. This one was done, okay, for research, but also because it was requested for a company that manages the municipal solid waste in Great Porto in Portugal, okay? And their doubt was they have a typical combustion process and they would like to know how will cost to change this to gasification. So first of all, we have to understand how the process is in a larger scale. And please notice that now the reactor is the double size of the other. This is a big setup that we have in Portoalegre in a special warehouse where we can get 250 kilowatts and gives us an idea as a pre-step for modeling the industrial process itself that could be in the range of megawatts, okay? And once again, what we have done here in a larger scale is try to understand the hydrodynamics, how the particles interact, because depending on interaction, we can understand how we can optimize the entire process. This is very interesting because if we feed the oxygen with different velocities, we have a completely different distribution of particles in the reactor. For example, if the velocity is higher than 0.4, we have a great dispersion that is not required in the process. But also, if we have a small velocity, maybe we are not promoting the interaction between the particles to react so well as we would like to. So this is why it is important. We want to potentiate the reaction itself to get more products, but at the same time, we cannot exaggerate the velocity condition, because if we have a great dispersion inside the reactor, the output will be not very good. So this is why it is so important to proceed with numerical simulation, because when we provide only experimental data on this, we will spend a lot of euros or dollars as we want. And with numerical simulation, it is very cheaper. And that's why companies prefer that. Let's say that this simulation at 2 dimensions take about 9 hours to do. And if we go to a 3-dimensional model, it can take 1 week, more or less. So this is a complex process, but still it provides a good idea about what is happening inside the reactor, and also provide the guidelines to optimize the entire process. And what we have done in this set of works is later to compare the better conditions in each case. Because when we go to the industry partners, they want the better conditions for their process itself. And what we discover, as expected, is that when we have a small reactor, the behavior of the particles is very different when we scale up it. So we had to do this kind of simulation for different sized reactors to understand how we can model the industrial reactor that is in the range of megawatts. And with this, we had the perfect knowledge of how we can scale up the entire process, not only in terms of the operating conditions, the kind of feedstock we can use, and also how to predict a big reactor that is very different than a small one that is used in the lab. So this is how we did this approach and how we can pass from the research to the industrial partners to be funded. This is a great example of that. One big question that many students ask is why you should use two-dimensional or three-dimensional models. What is better solution? It depends. If you want a great level of resolution, you should go for a 3D approach. However, a 3D approach takes much more time and it is more expensive in terms of time of simulation. So the great majority of times when we provided two-dimension simulation, it's enough. Even when we are dealing with big reactors, for example. And also we have some tricks to use a 3D simulation, but taking advantage, for example, of symmetry of the reactor. And then we reduce the time needed to do the entire process. So this is an example between 2 dimensions and 3 dimensions. And what is important here is try to understand first what is the best option. In most of cases, it is 2D simulations because the differences are not so wide. And if we want to design or if we want to understand what is happening, 2 dimensions is okay. If we really need a very, very, very accurate result, so we should go to 3D as a last option, okay? Because it will take too much time and sometimes to have just 2 or 3% of improvement, what in a big complex process in the industry is not nothing, because sometimes we have errors in terms of 5 to 10%. So pass from 2D or 3D, the gain is not enough to compensate all the time we take to do it. So, and after understanding the entire process, what we do next is to try to optimize the operating conditions. We understand that, for example, temperature, airflow rate were very important parameters. So we do optimization statistical method at different operating conditions, and we can understand which is the right value for each one of these parameters. For example, if we want to produce more hydrogen, we know that we should use the temperature around 700 degrees and 40 meters per hour. So if we want to optimize cold gas efficiency, in this case, it was at the same operating conditions. But many times we have to do a balance between the outputs we intend to optimize, because the optimum spot occurs at different operating conditions. And so we develop some statistical methods that combine, and we can say that hydrogen, for example, is 6% of the total weight in our decision. We can define this kind of solutions and try to identify what is the best spot to operate reactor. We can do it for a reactor, but we can do it for any system that we intend to optimize. So it is a very powerful method to design. For example, in this case, we use it to design of experiments and Monte Carlo methods, statistical methods, and we can understand as a function of 3 different inputs where we should operate our reactor for a certain output. And as I said before, we can combine both and try to understand what is the best balanced response and conditions to operate. So this is really, really powerful. And I can tell you that I use this kind of methodologies in several industrial partners to optimize their processes. So it's something we can earn a lot of funds from industrial partners here in our group. Besides the optimization process, we also do technical economic analysis. And what we provide to the partners is try to understand for a certain type of feedstock, in this case, alive biomass, what should be the return of their investment? How many years they will take to have profit? For example, the payback period for a small gasification facility should be about, in this case, 70 years. So this gives the final client one idea if they should move on this direction or not. For example, if they want to change their current facility for a different technology, if it makes sense, and how much time they will have to wait to have some profit, and also with which is our return of investment. So we try to use the numerical data, the experimental data, the optimization process, and then we can provide direct information to them about their own investment. So we try to provide the entire process to the industrial partners in order that they know we can do not only the technical part, but also the economic part. So in our group, we have people that has a strong expertise in the technical parts, but also some people that deals with the economic issues. This is another example. There was a great discussion in Portugal if our power plants with biomass should be at 1 megawatt and scattered along Portugal, or if we should select, for example, just a few power plants, but with a large capacity, about 10 to 15 megawatts. And what we have done was to study in terms of technical and economic aspects if it would make any sense to have so big facilities in Portugal. And what we have discovered is that was not a good solution because we do not have enough biomass to feed for a continuous operation in such a facility. So the best solution was to have different small facilities scattered along Portugal where we could supply enough biomass to each of them for a normal operation. This work was published in 2019, but we did this study about 3 years before, and it was proud for us because our government followed these kind of indications and changed their first thoughts about the direction of the size of the facilities that they would like to invest in Portugal. So this is a real scenario where we can help public entities, the government, to decide about environmental solutions that could have impact in all citizens. In a different way now, this is a simulation that we have done with a turbine and how we can understand the temperature, for example, inside a turbine, a reactor, and wherever, with different kinds of fuels. We can use ammonia, we can use diesel, gasoline, and then we can understand everything what is happening inside the reactor. For example, the temperature, the pressure, delivered power, everything. So this is very interesting for us because what we are trying to do is, for example, mixing different kinds of fuels and try to understand if is it feasible or not in certain kind of transportation, for example. So with numerical simulation, we avoid spending lots of money and we can understand with a great accuracy what is the best feed conditions, how we should feed the fuel inside the turbine or the reactor, etc., and try to optimize their process. We are doing, for example, this kind of studies for maritime ships because they are planning to use ammonia in their engines. So this is a very real thing that we will be in next years in the industry. So this is our system that we have in Portoalegre, the entire system. We have a feed system, the reactor, that one we provide simulation some slides ago. Just to tell you that this kind of facility that we have in Portoalegre has a cost more or less of $500,000, but it is very helpful because sometimes we can use it for the industrial partners. And as they do not have the chance to perform different operating conditions at their facilities, they can do such experiments here in a semi-industrial facility. So this is very interesting for us because it gives the opportunity to do some experimentation that is very close to the real ones. Also, we did it to understand the probability here in this project for Azores, that is an island, an archipelago in Portugal, and try to understand how a facility of gasification could be feasible or not to help in providing energy. So, as I was saying before about the fuels, we have here the example of what we do in simulation. In this case, is with ammonia, and we try to understand every step that is occurring with the combustion of the fuel inside the engine and try to understand the better operating conditions. It's not very usual to use ammonia because its kinetics is a bit slow, but if you understand correctly the hydrodynamics and if you use a good catalyst, it could have a performance that is not far away from typical diesel and gasoline, with the obvious advantage that if we have green ammonia, that we have a better environmental solution. So we did also a technical, once again, a technical economical study regarding the use of a 1 megawatt biomass to ammonia gasification power plant. This is another solution that is looked for industrial partners to understand if it makes sense to produce clean ammonia from biomass. In general, clean ammonia is produced through electrolysis, but also because it is a mature technology that the electrolysis itself, they are also looking for alternative options. And what we provided once again, it's to give them the information for 1 megawatt, what should be a return of investment, their payback time, etc. And what we discovered that is when integrated in current facilities that are using some kind of biomass, we can have a very interesting in terms of profit solution doing green ammonia from biomass. Once again, just to show you a little bit of how we do the simulation, and this one is to do regarding internal combustion engines, and this is a topic of interest that I would like to share with you. When we have some interest in a particle zone in the reactor, we divided the reactor in millions of cells. Each cell has a lot of equations, chemical reactions, heat transfer, mass transfer, etc. So with our numerical simulation, what we do is to solve this set of equations in each little cell, and then we go to the other and the other and the other. At the end, we have to provide a final value that is consistent across the entire value chain of these cells. So this is why the process takes a lot of time, and it is very important to understand first the process, because we need to depart from very interesting conditions, because otherwise, if we can arbitrate random values, it will be very difficult to converge the solution. So it's not enough to know how to use the software, for example, but it is very important to understand the process, to provide good values to start the evaluation, and if needed, to provide code, in-house code, to correct the commercial software packages and try to reach a good solution. So with this kind of works, we publish in a lot of well-known journals. If you can see from here, it's very focused on energy topic, and also as we can provide environmental clean solution. So we submit a lot of papers in cleaner production, renewable energy, applied energy, energy conversion and management. It's the kind of journal I try that all my students could publish, because it's a very good way for disseminate our work. Also, we didn't do everything alone, and I try many times to partner with several individuals or institutions across the world. Unfortunately, we have strong ties with universities that are very well known, like MIT, Stanford, Technion, Politecnico de Madrid, because we try to get from them some parts where we are not so strong or experts, and we provide instead our expertise and try to combine the best of both institutions. So that's more or less our strategy, and I'm very happy with it because we learn a lot with each one of these institutions. Thank you for your attention, and please be free to make any question. Thank you.